So yeah, the topic of the talk was already introduced, and basically what I'm going to explain in the beginning is what is eBPF, because that's the technology which BTF debug format is for, and how it differs from kernel modules, because you know, previously on this conference we had one amazing workshop and talk about Rust for Linux, which is basically a project bringing Rust to Linux kernel modules. And because of that, I'll explain also a difference how eBPF differs from kernel modules, and how what I'm talking about is different from what was spoken about previously. And yeah, important info here is that eBPF is something where already since many years you can write them in Rust. But there is still some work to be done to achieve completely 100% feature parity with eBPF in C. So that's what I'm going to talk about. So yeah, as I briefly mentioned, there are two ways of extending the Linux kernel. One of them are kernel modules, and that's what Rust for Linux is for. And there are eBPF programs, and that's what IA is for. And the difference that kernel modules have full access to the kernel internals, and you actually need the kernel source tree to build your kernel module. When you write your kernel module, of course, you can keep it in your own Git repository out of tree, but it's very encouraged to submit it to the upstream kernel repository, and the most of drivers are the mainline kernel repo. The important thing to note is that when you write a kernel module, you don't only have a full access to the kernel internals, but if you do something wrong, you can also crash the kernel. But that's necessary, and I would say that from my perspective, kernel modules are great for device drivers or writing a new file system or anything which extends the kernel functionality like directly, like completely new features in the kernel. Okay, kernel modules are a good fit for that. eBPF is something different, and eBPF allows you to extend kernel modules, but with your completely third-party project. And you don't need even kernel sources to build such a project. You just need a compiler which supports BPF, and the BPF support first appeared in LLVM. It's also in GCC now. Because it's in LLVM, therefore it's in Rust as well. Like every LLVM frontend, if they want, they can add support for BPF target, but for now it's Clang and Rust. The great thing about eBPF is that it cannot crash the kernel unless there is something wrong in the BPF mechanism itself. But in theory, and most of the time in practice, your BPF program is not able to crash the kernel. Even if you write bad code there, it's going to be, you know, it's going to affect only your logic, but it's not going to shut the whole system down. And that's why it's a great fit for third-party tools which hook into Linux kernel internals, like firewalls, tracers, and security monitors. So it's perfect for debugging, and it's perfect for detecting what's happening in the system and preventing bad activity. Well, like you might be wondering why eBPF cannot crash and how it happens that only some hooks of the kernel are exposed to BPF, but not the whole internals. So it's a virtual machine. So actually, kernel is running like a very small virtual machine inside it, and it's just extending those hooks to it. And that virtual machine comes with its completely own assembly architecture. It's very constrained, so there are 8 registers there, and there is a limit of BPF assembly instructions you can execute. For now, it's 1 million. And it's done on purpose. So it's done on purpose that your BPF programs have to be small. They just need to hook into some event the kernel, process it very fast, get the data you're interested in, dump it somewhere, and then be done. Like this way, we are preventing writing too much logic embedding too much logic into your BPF programs. And since BPF is a virtual machine, it has its own assembly. That's why compilers need to support that assembly language. And LLVM was first. GCC is there. We are using LLVM here. Just for quick comparison, like on the left, you have like standard kernel modules in Rust for Linux, which is a project in the kernel modules world, and on the right side, you have eBPF, which is the main official library for writing BPF programs, which uses C. It's designed to write programs in C and compile them with Clang or GCC. And the last logo, like the mutation of B and crab, is a logo of Aya. B is a logo of BPF, so to merge the Rust and BPF, we have this cute crabby. You can visit the website. And amazing thing is that to start with Aya and start writing your own small firewall or security tool or debugging tool for your system, the only thing you need by default, if you are not doing anything too difficult, is RustLab and Cargo, and you should be ready to go and ready to code. And one of the prominent projects using Aya is a tool called Pulsar, which is developed by Exane, and it's a lightweight security monitor designed mostly with IoT devices in mind. But even though it's designed mostly for IoT, it works on x86 as well. But like we are just taking care of keeping it small and always making sure that it compiles on multiple architectures. And little demo how BPF works. So I have two examples of little BPF programs. First of them is just tracing your own network packets. So like this Rust program, it's basically receiving that context, and that context is given by the kernel. And when we run this project, it's just going to show all the packets, all the ingress packets which are incoming to your machine. But tracing is tracing, but we would like to sometimes prevent stuff from happening, right? So the next stage of writing your BPF program is actually preventing. For now, you could see that I could access the 111 address, and we will try to block the traffic coming from 111. So we will block the response coming from 111. And we see action 2 means it's allowed, action 1 means it's denied. And we can see on the logs on the left that traffic incoming from 1111 was denied. And on the right side, we could indeed see that our curl command was hanging. So getting back to the slides. And before I dig further, I need to introduce one compiler-related concept, which is debug info. And debug info is metadata generated by compilers about your code and stored alongside the binary. This is basically what debuggers use for showing you the information which line of code you are in. So if you are running LLDB, for example, to debug your Rust code. The reason why are you able to see the exact line you are in and jump to next one and so on is that when you compile your program with the debug flag, then it embeds the information about each line, each type, each variable to the sections corresponding to the sections of your code. That it's embedded in the binary. But yeah, debugging is one of the use cases, but there is also another use case which is important in BPF. And when you are writing BPF programs, you very often want to handle some kernel structures. You basically want to get some event from the kernel, figure out what's happening, and sometimes in order to do that, you need to get an access to some kernel structures. And the problem is that they can change. There is no guarantee in kernel structs to be stable. It's quite the opposite. It happens very often that they change. And as I mentioned when pointing out the difference between BPF and kernel modules is that when you are building your BPF program, you don't need kernel sources, first of all. And second of all, you shouldn't require certain kernel version. Like in theory, you should build your program and be able to ship it to every kernel version, which meets some basic requirements, but you shouldn't care about building your BPF program on kernel 5.5 and shipping it to kernel 5.9, for example. But how is that handled? Like, because those structs changed so often. We use debug info for that. So debug info contains all the information about how a certain type, struct, or union looks like. So we can pretty much use it to figure out when we want to access a field of some struct, where exactly in the currently running kernel it is present. But here's one problem. So the most popular debugging format, which is the one being used in debuggers, is dwarf. It is really huge. For bigger programs, it can take megabytes, even dozens or hundreds of megabytes. It contains a lot of information. And really to figure out just offsets for structs or unions we want to access and to handle differences between kernel versions, you don't need all the information that dwarf provides. So that's why kernel developers came with their own debug format, which is called BTF. It's basically like, think of it as a minimized version of dwarf, which basically just is able to list the types, and if the type is struct or union, it shows you the elements of it with offsets and their types and sizes. A bit of compiler theory. Both Clang and RustC are LLVM frontends, and how compilation of your program happens is that if you are using Rust, then your Rust code is firstly parsed, like compiler is parsing the tokens. It has the high immediate representation, immediate representation, which are internal Rust representation. It's just how Rust figures out the structure of code. But then to produce the actual binary, Rust is using LLVM. And LLVM, in order to support different compiler frontends, it has something called IR, which stands for immediate representation. And I think the best way to describe LLVM IR is that something in between like C and assembly. It's not machine specific, but it's primitive enough language to be kind of universal and to be super easy for compiler backends created for each CPU architecture to just convert it to the machine code without worrying about some special some special things implemented in the language. So IR is like, you know, the last step before the machine code. Alongside IR, you have also LLVM debug info, which is also a representation of you know, the debug info I mentioned, which is the last step before converting into the final format like dwarf or BTF. So when you have the last step, machine code plus DI, the conversion to either BTF or dwarf happens at that exact last state. And before that, it's just LLVM DI format. LLVM debug info format is, like, I would say, compatible with dwarf. Sometimes people even just call it dwarf, but yeah, LLVM produces dwarf, but well, it's compatible. If you dig into LLVM API internals, they have their own class structures and hierarchy to describe the debug information of your code. And it looks somehow like this. So, well, the first step in the middle, when you have LLVM IR, is this kind of still like human readable. It's text format, you can read it. Bitcode is still an immediate representation, but in binary format. So when you have bitcodes, like, and if you open it with a text editor, you will receive junk. But on the first step in the middle, when you open the LLVM IR file, so something that Rust or Clang produce, and go to lines with debug info, you basically receive this. So you can see that you have a structure type, you have the name of it, there is a reference to file, and if you dig into IR, there will be information about which file was it, which line, and then there is a pointer to elements, and in the second line you have a list of operands, which are elements of the structure. And then you have fields of the struct, which are basically yeah, integers, and you have pointers to the base type. And if you dig into IR, you would see that those base types are, for example, U32 or I32, like signed or I-signed integers. And at the end, BTF looks like this. So it doesn't contain those the information about files anymore. As I mentioned previously, it's basically name of the name, type, offset, size type of thing. And that's enough for the kernel to figure out yeah, how to access the field of the union struct. So when we have this debug information, LLVM has an intrinsic. So it has a function which you can call in LLVM IR, and it's called preserve access index. And its signature looks like this. I mean, there is a separate version of the intrinsics for union and for struct, and also for arrays there is one. And yeah, you don't have to like fully understand it, but the idea is that if your BTF compatible code gets dumped to IR, you eventually end up with this compiler intrinsic where the pointer to your struct is being provided, and then index to the field you want to access, and the index of that field in the debug info, which is the last DI index parameter. To show you some example, let's imagine that there is some struct, let's call it my struct, and in older kernel version, let's say 5.5, it has just two unsigned integer fields, and then kernel developers add a new field in the newer kernel version, and to make it even harder, they insert it just in the middle, not at the end of the struct, but just in the middle. Yeah, thanks to embedding BTF in the BPF program, when you compile the program on your machine, on the older kernel, you receive what's on the left. But then when you load it to the newer kernel has its own BTF information about all the structure it has, so it's then able to compare and do the relocation. So then when you load, even though, in your BPF program on your machine, the offset of the field is 32, kernel will be able to figure out, I have fields in the middle, like I'll use the offset 64 to access that field. And unfortunately, supporting that mechanism was, and still is, I hope for a very short time, feature gap in IA and writing BPF programs in Rust. First reason why is that Rust doesn't support the preserve access index intrinsic, so there's some work to be done there. But then the other obstacle was that even though in theory Rust is using LLVM as compiler backend, and you should be just able to, enable debug info, use the debug equals to option, and that should produce BTF. That works. Although at the beginning we found some bugs in LLVM that's, like the debug info being produced from Rust code was crashing the BTF backend. So first of all, there were some bugs in LLVM to be fixed. But after getting rid of that, we had problems with loading those programs into the kernel. And the thing is that the kernel has certain assumptions about how types look like. And BPF and BTF were written with C in mind. It comes out that for the BTF interpreter in the kernel, Rust types were confusing. So for example, in Rust, we have data carrying enums, so we can write enum, which has an embedded struct or tuple and carries other types inside. LLVM debug info supports it, but when LLVM DI is lowered to BTF, and then loaded into the kernel was confused, was like, what is this? Like, I'm not supporting this. The other thing is that Rust type names are not always alphanumeric. So for example, if you use generics in Rust, so you have something embedding the generic T type, then the types being finally produced after compilations contains those brackets and the names of types they are implemented for. That's also annoying for the kernel. It expects all the type names to be purely alphanumeric. So, and also it has length limits. So the name types which you are loading in BTF to the kernel cannot exceed 128 characters, and with Rust and long paths, long generic names, you can reach that limit, because at the end, very often in the debug info of produced by Rust, you have the whole path, package by package, and then the type name at the end. So yeah. We have to sanitize it and also trim it down to 128. And when we are trimming down, of course, we are appending a small hash at the end to avoid collisions. But also, the other problem is that kernel is not only annoyed by Rust types, but it also expects something which Rust doesn't support. And the thing is that it sometimes requires certain types to be anonymous, and in Rust you cannot have anonymous structs. So to give more context, in BPF there is a concept of BPF maps. They are basically hash maps and other data structures which are shared between BPF kernel space and the user space. For some reason, kernel requires structures defining those maps to be anonymous, which Rust can't do. How we overcome it is that we add a marker to BPF map types and then let know that, okay, you have to strip the name here. And well, I would say that there are two stages to bring the support of BTF to the Rust compiler. The first stage is happening and it's close to be done, sanitizing LLVM debug info in order to not annoy the kernel. And the second stage will be, once the first stage is completely done and proved to be working, to contribute to the Rust compiler to support preserve access index intrinsic. And more details about sanitizing. So there is a project called BPF-linker, which is being used when you compile BPF programs in Rust. So basically in BPF-linker, we are modifying the debug info to meet the expectations. And to explain a bit what BPF-linker is, so BPF-linker is a bitcode linker. So when we go back to the stages of LLVM compilation, so it works on the almost last stage, LLVM BC. And so, you know, when you have different crates in Rust, you first build bitcode objects from them, and then BPF-linker is taking care of creating a final object file from them. And that's a good stage to modify debug info in, because at this stage, yeah, we know we still have LLVM debug info, not BTF or dwarf. So using LLVM API, we can still modify it. So yeah, like we figured out that's the best place to do that. And a bit of context why BPF-linker was created in the first place. It wasn't for BTF, it was because of something else. Usually when you write BPF programs in C, linking is optional, but almost nobody does that. So like in the most prominent projects in BPF projects written in C, how embedding some common code is done is usually by headers. Like, yeah, I don't know any big BPF projects written in C using linking. But it's not the case in Rust. In Rust, linking is mandatory. Even when you use the no STD option, which we do for BPF programs, you have a core library, which is fine to use in BPF context, so we are using it. It's a separate crate, you have to link it. And so there is no way to get away from linking it all in Rust. So that's why, since the beginning of BPF support in Rust, BPF-linker was there to serve this purpose, and now it's going to serve the other purpose, sanitizing the debug information as well. The work in progress for the BTF sanitization is already in BPF-linker repo in feature fixDI branch. We are really hoping to release it soon. It mostly works. There is like one tiny bug to fix before we can carry on, and also an ongoing work which we are doing is really coming up with spectrum of tests, testing all the Rust types and checking whether they are properly sanitized. Once that happens, I think we will be good to go with releasing BPF-linker. And also the other thing, it's a bit minor, but what we want to do before making the next BPF-linker release is linking libLLVM statically, because for now, BPF-linker requires LLVM, and there are two ways of providing LLVM to it. First, which works on the most of machines, is that BPF-linker is trying to find the libLLVM.so shared library in your Rust installation, and on x86 Rusty is providing libLLVM.so file. It doesn't work for any other architectures. So in all the other architectures, Rust C comes with statically linked LLVM. So we want to do the same. We want to also have static libLLVM statically linked into BPF-linker to not bother people with installing LLVM on their machine. And yeah, once that's done, the first stage of bringing BTF support is going to be closed. And then the second stage will be providing preserve access index, and that will require, first of all, calling the LLVM intrinsic in the Rust C codegen LLVM, and then adding it to Rust core intrinsic. So like 2 subcrates of Rust compiler are going to be affected by this change. And then long term, in theory, correct solution, because what I was talking previously about is very hacky. Maybe some of you are already wondering, like, why is it so hacky? Why are you doing this? We are aware that the long-term solution would be teaching kernel to accept non-C types. But first of all, I think it makes sense to do it once the sanitization option is done and proven to be working, and we know all the surprises we can expect from getting BTF to work on Rust. And also the other thing is that I think it would make sense to start teaching kernel about Rust types once Rust for Linux will be interested in that work as well. And for a bit of a context, when you are driving your kernel module and you define some types there, you usually build BTF for them as well. And that it isn't supported in Rust for Linux yet. So when you build your driver in Rust for Linux, you cannot build BTF. So yeah, I think that once this hacky previous solution is going to work for BPF and IA, the next stage will be collaboration with Rust for Linux and trying to enable BTF there, and also at the same time make changes to the kernel in order to accept more complex types. Good thing is that Linux is a monorepo, so it will be very transparent to see the change across Rust for Linux modules and across the BPF subsystem code. Also, the other thing which would be nice to teach Rust would be to have some option or flag in cargo to just tell Rust to emit only BTF, other way than debug equals to. Maybe some of you have questioned why didn't we go with this correct long-term solution first? And the answer is that it's going to take a lot of time, many years, if that happens, to get it into LTS kernels and LTS distributions. And people want to use BTF here and now. People want to load their BPF programs in some old Debian versions and like 5-point-something kernels or even 4-point-something kernels, although in 4-point-something BTF wouldn't work. But yeah, like people don't want to wait years for new kernels to arrive. So yeah, that's why it's done in this order. And at this point, I would like to thank you for listening. And do you have any questions?
Okay. Thank you. Okay. So if you have any questions, you can raise your hand and or share your thoughts, comments, or everything is clear.
I hope so, yeah.
Okay.
Oh,
okay.
Nice.
We have
one. So one question, if you ignore the Rust initiative to get Rust code into the Linux kernel, are there actually cases where it would be a problem that there is no support for Rust types in BTF? Because you would compile Rust code to BPF code, and you would just talk with kernel structures which are written in C. So it's actually not clear to me where it would actually be a problem that there's no support for the Rust types there.
When you write your own structures in your BPF program, the BTF info is generated also for them.
Ah, okay.
So that's the problem. And you very often want to have your internal structs. forbidding you from having data carrying enum would be a bummer, because honestly, that's one of the advantages. What I noticed about people writing BPF in Rust is they are so happy that they can match over some data carrying enum expressions. Yeah, taking away that wouldn't be that great.
Makes sense. Thanks.
Thank you for the talk. This is just meant for debugging, right? It's not like I can conditionally load BPF code depending on at runtime, depending on the availability of, for example, a private field of a struct.
You can actually do that. So there are macros for that in libbpf, and once we introduce the preserve access index intrinsic in Rust, it would be great to add them to Rust as well.
Okay.
So yeah, it's possible to use BTF to also figure out in your code in runtime that if such field exists, only access it.
Okay, thank you. Because basically the problem is I load my BPF module into BPF program into modern kernel version, and I want to target also another host that maybe has an older version. So it's actually possible. Thank you.
It is. So this is the example. So you can conditionally check whether it exists. The main macro used for accessing fields in BPF is called BPF core reads. And when the field doesn't exist, it's just going to return you null, and you need to handle the case of having a null pointer. But yeah, like this other macro I showed allows you to conditionally check.
Great. Thank you.
You're welcome.
Okay, so thank you, Michal. Thank you for attending this talk. I guess we can prepare ourselves to have lunch if you if you want to. Thank you very much. Thank you. Thank you.